everyone, this is Miss Afric here, and today we're going to be talking about simplifying radicals. And that's actually going to be our first goal too, so go ahead and copy that down on your notes. That goal number 1 is going to be to simplify radicals exactly. Okay, now be careful about this last word, exactly. What that means is we do not want decimals. No decimals. Unless it says specifically to approximate, we do not want decimals. Okay, we know that it's really easy to just pull up your calculator and type in the square root of 32 and then press enter and get this decimal, right? But that's not what we want you to do. If we wanted you to do that, we wouldn't spend this whole lesson doing it. Alright, so make sure that you are simplifying these radicals exactly. Okay, and when we talk about a radical, the radical symbol is just this root symbol right there is another name for it. And just remember, when there's no number on this little part right here, that means it's really just a 2, which means it's a square root. Okay, so you'll never see the 2 there. It's like an invisible 2. It'll just look like that. But just know that when there's no number there, it's a square root. Okay, let's go ahead and try some examples. Alright, so in example 1, simplify the radicals. The first one we've got is the square root of 32. The way we're going to simplify this is by factoring it completely. We're going to get it down to what's called prime factorization. Okay, so I'm going to factor this. 32 I know factors into 2 and 16. And I know 16 factors into 4 and 4. Okay, and then each 4 factors into a 2 and a 2. Okay, now I'm going to bring this other 2 down because I can't factor that anymore, but it's still part of it. And these 5 2's here are known as the prime factorization of 32. Okay, and once we have it completely factored, what we do is, because it's a square root, a 2, right, we look for pairs of the same number. So here I've got a pair of 2's, and here I've got another pair of 2's. Alright, and then for every pair that you find, you get to pull one of those numbers out. So if I have a pair of 2's here, I get to pull 1 2 out. And just to be clear where that's coming from this pair of 2's. Alright, I have another pair of 2's right here, so I'm going to pull another 2 out. Okay, and then I'm left with this 2 that doesn't have a pair, and that means that 2 gets to go on the inside, or underneath the radical. Okay, so every pair gets one of it to come out, and then when it's left over, it stays on the inside. And then I simplify this. 2 times 2 is 4, so 4 times the square root of 2. And that's my final answer. Take a look at letter B. Letter B is similar, except there's a number on the outside. Alright, we've got this 2 on the outside already. That's fine. We're just going to go ahead and keep that 2 on the outside, and then factor the square root of 125 off to the side, and then bring that answer back. Okay. One thing you always want to check is that the number underneath your radical isn't already a perfect square. Because if it's a perfect square, it makes your life a lot easier. Okay, so I'm going to just check that real quick. Square root of 125. Well, because I got a decimal, I know it's not a perfect square, so I'm going to go ahead and factor it out. 125 factors into 5 and 25, and then 25 factors into 5 and 5. If I bring that down, now I've got my prime factorization. Every pair, I get to pull 1 out, so I get to pull a 5 out, and then this 5 is left underneath. Oops. Alright, for every pair I pull 1 out, that 5's left underneath the square root. So I'm left with 2 times 5 times the square root of 5. Now remember, we multiply numbers on the outside, so that's going to give me 10 times the square root of 5. Okay, let's try some harder problems. So if I scroll down here, you can see we've got a couple of properties that we're going to be using. The product property and the quotient property. Product property deals with multiplying numbers and how I can split it up into 2 separate radicals that are still being multiplied. And then the quotient property deals with splitting up division. So I'm dividing 2 numbers underneath one radical, and I can split it up into 2 separate radicals. So let's use these properties in these examples here. Letter A says the square root of 10 times the square root of 15. According to my product property, I can go ahead and combine that. So I've got the square root of 10 times 15. 10 times 15 is 150. Okay, so now I just have the square root of 150. Now, you should check on your calculator, but 150 is not a perfect square. So I'm going to go ahead and simplify that by factoring it out. Okay, 150, well, they already kind of told me here that it factors into 10 and 15, so that's nice. And then we've got 2 and 5, and over here we have 5 and 3. Okay, these are all the prime factors, so I see a pair here of 5s that I can bring out, and then I see a 2 and a 3 that's left over. Okay, because they don't have another pair that's identical to it, it has to stay underneath. So this is going to leave me with 5 times the square root of 6 when I simplify this. Alright, letter B is pretty similar, except it's got some numbers on the outside. Okay, so again, just like the example we did above, I'm just going to take those numbers and multiply them on the outside. And then the numbers on the inside, this 8, this 18, and this 4, I'm going to leave on the inside. So 8 times 18 times 4. And then it just becomes a normal problem. We can go ahead and simplify both the numbers on the outside and the numbers on the inside. Alright, and I think you guys can do this on your own, so go ahead and try that. Pause the video to make sure you did it correctly. Okay, pause it right now and try it. Alright, well hopefully you tried it and you should have gotten 480. That number underneath the radical ended up being a perfect square, which gave us that answer. Okay, if you didn't get it, go back and check your work, see where you went wrong. Alright, letter C. Letter C, we're going to go ahead and use the quotient property. Remember, the quotient property says we can split this up into 2 separate radicals that we're dividing. So, I'm going to split this up. Square root of 27 on top, divided by the square root of 49. Okay, hopefully we recognize that although 27 is not a perfect square, 49 is, and the square root of 49 is 7. Okay, and then if I go ahead and simplify the square root of 27, I know this is going to break up into 9 and 3, and then the 9 breaks up into 3 and 3. So I have these here as my prime factorization. I can pull out a 3. So I end up with a final answer of 3 root 3 divided by 7. Okay, let's move on to another new idea, which is something called imaginary numbers. Now, all of your math career, you've been dealing with the idea that there are only real numbers, but there are actually another type of number that you haven't seen quite yet, and that's called imaginary numbers. Okay, and imaginary numbers occur when you have negative numbers underneath a square root. Okay, so I'm going to jot that down. Negative numbers under a square root. So in other words, when you take the square root, root of a number, or of a negative number, you end up with an imaginary number. And it actually happens when you take even roots, so square root, fourth root, sixth root, but we haven't dealt with those yet, so let's just focus on square root. Let's keep it simple. Okay, so something like the square root of negative 9, the square root of negative 11. All right, those are all imaginary numbers. And what we say is the square root of negative 1 is equal to I, and we let I just represent an imaginary number. Okay, and then another important fact that we're going to use later on is if I square both sides here, I actually get the square root, oops, I wrote that wrong. I get the square root of negative 1 squared, and then I squared. And a square undoes the square root, so I actually end up with this really important fact here. And that fact is that I squared is equal to negative 1. Okay, we're going to use that a lot later, so that's a good one to know. Alright, let's try some examples together with these imaginary numbers. Okay, in letter G, we're going to simplify the radical, the square root of negative 45. Now, the way we deal with imaginary numbers is we actually start by pulling out a square root of negative 1, because we know what the square root of negative 1 is equal to. It's equal to I. So I'm going to pull that out first, and when I pull that out, I'm just left with the square root of 45. Okay, and the square root of negative 1, well, that's I. And then the square root of 45, that's just something I have to simplify. So the square root of 45 over here, and we're going to simplify it the same way we have been. Nothing changes about that. So it breaks up into 9 and 5. 9 breaks up into 3 and 3. Okay, I've got a pair of 3's here, so this is going to be 3 root 5. So I've got I times 3 root 5. But I don't want to leave it like that because when I have numbers on the outside, I always like the number to come first and then the I. Just like with variables, how x comes second, it goes 3x, not x times 3. Same idea here. So I'm going to write this as 3I times root 5. And that's my final answer. Okay. For letter H, same idea. I'm going to start by pulling out a -1. That leaves me with the square root of 16, so I have the square root of -1. Remember, I can't pull the -1 outside of the square root, so I'm really just breaking it up into the square root of -1 times the square root of 16. So I apologize for the wording. That's probably confusing. Let's not say pulling out a -1. Instead, let's just say we're breaking it up. And then the square root of -1, that's going to become an I. And the square root of 16, well, that is actually a perfect square, 16, so that's just 4. But then again, I want to rewrite this so it's in the right order, so I've got 4I. Alright, this example down here, letter I, is a really good one, so let's check that one out. Okay, square root of -4 divided by 3. Well, the first thing I want to do is use that quotient property to split this up into the square root of -4 divided by the square root of 3. Okay, and now I have that imaginary number on top, so I'm going to break that up into the square root of -1 times the square root of 4 divided by square root of 3. Okay, and that top part, this becomes I, and the square root of 4 becomes 2, so this gives me 2I divided by the square root of 3. Now right here, you can't leave this as your answer, and this is an important fact that we're going to learn, and that fact is, and hopefully you've heard of it before, we can never leave a radical underneath the square root, or underneath the fraction. We can, geez, I'm all tongue-tied here. Never leave a radical under a fraction. So let's say that differently. Never leave a radical in the denominator. That is the word I'm looking for. Never leave a radical in the denominator. Okay, so what we have to do instead is rationalize this. And the way I'm going to rationalize this is by multiplying the top and the bottom by that square root, by that radical 3. Because what happens is on the top, I'm just left with 2I root 3, but on the bottom, root 3 times root 3 is just 3. So that gets rid of our radical. Okay, the second goal we've got for the rest of this is to perform operations on complex numbers. Now when we talk about complex numbers, all that means is it's part real and part imaginary. Okay? So we're going to see numbers like this, and it's like these numbers here that you see in A, B, and C. Those numbers are all complex because it has a real part right here, and then it has an imaginary part, the part with I. Okay, now we're going to go over how to plot these numbers in class. We're going to talk about that in class because that's not too bad. But I want to get to some of these operations that are on the next page. So go ahead and flip your page over. Okay, for these, we're going to write the expression as a complex number in standard form. Now, standard form for complex numbers means A plus BI. So it means, in other words, the real part comes first. Oops. Okay, the real part should come first, and then the imaginary part should come second. Okay, so let's try some of these. In part A, 3 plus 2I plus -5 plus 8I. Now, when we're adding or subtracting complex numbers, it's actually nice. You're just combining like terms. So I'm going to add the real numbers because I'm adding here. All right, I'm going to add those real numbers. So 3 plus -5 is -2. And then I'm still adding. Now I'm going to add my imaginary numbers. 2I plus 8I is 10I. And that's my final answer. All right. Similar thing for letter B. The only difference is letter B we are subtracting. So I have to be careful here and make sure that I'm subtracting these numbers. So I'm going to do, and I'm going to write this out just to be careful, 5 minus 2 first, and then -8I minus 9I. So -8I minus 9I. Okay, and that's going to give me 3 minus 17I. And these are in standard form, so I know I'm good. Alright, for letter C, when there's no plus or minus in between here, in between these two sets of parentheses, that means we're multiplying. So I'm going to multiply these two. And in case you've forgotten how to multiply the binomials like this, we have to go ahead and distribute both of these numbers. So I'm going to distribute 2 to both of them and 3i to both of them. Or sometimes you might know it as FOIL. Okay, so this becomes 2 times -6 plus 2 times -2i plus 3i times -6 plus 3i times -2i. Okay. Now, we're running out of time, so go ahead and try and simplify this on your own. And then see if you can do D on your own too. Okay, but save this one, E, save that for class. Hope you had fun.